All right, let's talk about something that's at the very heart of the liberal arts. I mean, we spend all our time analyzing arguments, deconstructing texts, building our own essays. But what if I told you there's a tool that can actually show you the hidden logical skeleton inside our everyday language? Well, today, we're going to pull back the curtain on that tool, the truth table. Let's just dive right in.
So, picture this. You've been there, right? This seems like a simple enough request, but common words like or, can be surprisingly slippery. Does this mean you can get one or the other, but not both? Or does that little word or leave the door open for that perfect couch that's a sectional and has a chase? In logic, you can't have that kind of ambiguity. Clarity is king, and this is exactly where our journey starts. And boom, this little table gives us a crystal clear answer. This is a basic truth table, and what it does is it maps out every single possibility. We use T for true and F for false. Now, look at that very first row. If the couch is a sectional, that's true. And it has a chase, also true. The whole statement, get a sectional or a chase, is still true. That's because in the world of logic, or is what we call inclusive. It means you can have one, the other, or hey, even both. As long as at least one of those conditions is met, you're good to go.
So here's our game plan. First, we're going to decode the basic symbols that logic uses. Think of it like a universal shorthand. Then, we'll look at the simple rule books for those symbols. After that, we get to the fun part. We'll build our own possibility map, a full truth table, to solve a much trickier problem. And finally, we'll bring it all home and see how this connects back to making you a stronger, clearer writer and thinker. Okay, first up, the symbols. Now, don't let this part scare you off. We're not learning some complex new language. Honestly, it's the opposite. Think of this as a super efficient shorthand. Its whole job is to cut through the messiness and ambiguity of everyday language, so we can see the pure, simple structure of an idea. Let's start with a classic, and. So, in logic, we use a capital letter to stand in for a whole idea. So, P can be our shorthand for I like Pepsi, and C can be I like Coke. To connect them with and, we use this little symbol right here that looks kind of like an A without the bar. So the whole sentence just becomes P and C. That symbol is technically called a conjunction, but really it just means and. That's it. And here is our good friend or. Using those same stand-ins, I like Pepsi or I like Coke gets written as PVC. This one's called a disjunction. And yeah, you guessed it, this is that same inclusive or from our couch example. It just means that at least one of these things has to be true. And finally, the easiest one of all, not, or what we call negation. To say, I do not like Pepsi, you just put this little squiggly symbol, it's called a tilde, right in front of the P. Just like that. P. All it does is flip whatever comes after it to its complete opposite.
So with these simple symbols, we can start building some pretty complex statements. And a truth table? Well, that's our ultimate tool for clarity. It's a way to systematically, methodically, check every single possible outcome of a statement to see exactly when it holds true and, more importantly, when it falls apart.
All right, let's move on. Now that we have our symbols, we need to know how they behave, right? We need a rule book. So think of these next few slides as the fundamental cheat sheets for all of logic. They're really simple, but everything else is built on them. Here's the rule for and. Look at this closely. The statement A and B is only true in one single case, when A is true and B is true. That's it. If either one of them is false, or if they're both false, the whole thing collapses. It just makes intuitive sense, right? The sentence, I like Pepsi and Coke, is only true if you actually like both of them. Now for or. This is basically the mirror image. A or B is only false in one situation, when both A and B are false. As long as at least one of them is true, the whole statement is considered true. And yep, that's our inclusive couch rule, right there in black and white. And the simplest rule on the board, not. This little guy just inverts the truth value. If A is true, then not A is false. If A is false, then not A is true. It's really just a logical light switch. On, off. Simple. Okay, we have our symbols, we have our rule books. Now we get to the really powerful part. We're going to combine all of this to build a complete truth table for a more complex, real-world kind of statement and see what truths we can uncover. This is where it all comes together. So here's our puzzle pulled from the world of sports. The condition for Anaheim making the playoffs is this: Anaheim wins its game, or Boston does not win its game.
Okay, let's translate this. Let's make Anaheim wins our statement A. We'll make Boston wins statement B. The statement connects them with an or, that's our V symbol, and a not, that's our psi symbol. So the logical shorthand for this whole thing is A, V, psi B. Now, building the table for this isn't some kind of magic. It's just a totally methodical process. We're just going to follow these 5 simple steps. The real key here, as you're about to see, is to work from the inside out. We solve the smallest, simplest parts of our statement first, and then we build up to the final answer.
Step 1. List every single possibility. Anaheim can win or they can lose, and Boston can win or they can lose. When you combine those, that gives us 4 unique scenarios. Both could win, Anaheim wins and Boston loses, Anaheim loses and Boston wins, or they both lose. We have to map out this entire universe of possibilities before we can do anything else. On to steps 2 and 3. So remember, we work inside out. The inner part of our statement is B, which means Boston does not win. So we make a new column just for that. Then, for each row, we just apply our super simple not rule to the B column. So wherever B is true, not B becomes false. And wherever B is false, not B becomes true. We're just flipping the values.
And now, the final step, the big reveal. We make our last column for the entire statement, A, V, shim, B. To figure this out, all we have to do is apply our OR rule, but we apply it to the A column and our new shim B column. Remember the rule, OR is only false when both parts are false. So let's just scan down, okay, and there it is, row 3. It's the only one where A is false and shim B is false. That is the single specific scenario where Anaheim doesn't make the playoffs. In every other possible reality, they're in.
So we just mapped out a sports scenario. Big deal, right? What does this have to do with writing an essay on Plato or analyzing a political speech? Well, it turns out everything. This tool goes way beyond math and computer code. At its core, it is all about clarity of thought. Learning this gives you a kind of analytical superpower, seriously. When you're reading a really dense philosopher or you're trying to deconstruct a politician's speech, this is the tool that lets you basically X-ray the text. You can map out all the if-thens and the either-ors and see if the argument actually holds up under pressure. It also forces you to check your own essays for logical gaps. It's not about the math, it's about making sure your arguments are built on solid ground. This really is the bedrock of critical thinking. So I'm going to leave you with this question. Think about a tricky philosophical concept you've been struggling with, or a legal clause, or maybe even a line from a poem that feels deliberately ambiguous. How could mapping out its logical possibilities, just like we did today, bring you a whole new level of understanding? The truth isn't always obvious, but with the right tools, it's always within reach.